Hi, my name is Ali Osborne, and this is my Physics 2211 Constant Velocity Lab. To start, I'll give a brief overview of what I'll be discussing. I'll begin with the fundamental physics principles, then explain the models used, describe the experiment, present the results, discuss the comparison, and finish with my conclusion. The purpose of this lab was to analyze the motion of an object moving at a constant velocity and to compare that with experimental data to a computational model based on fundamental physics principles. This lab is based on Newton's first and second laws of motion, along with the concept of constant velocity. Newton's first law, also known as the law of inertia, states that an object at rest stays at rest, and an object in motion continues to move with a constant velocity unless acted upon by a net external force. Newton's second law states that the net external force acting on an object equals the time rate of change of its momentum. In the case of constant mass, this simplifies to F net equals m times a. Constant velocity means an object moves in a straight line with a constant speed. If velocity is constant, acceleration is zero. And according to Newton's second law, if acceleration is zero, then the net force must also be zero. This idea is the foundation of this lab. There were two approaches used in this experiment, experimental and computational. For the experimental portion, I recorded a video of an object moving with constant velocity. I then uploaded the video into Tracker for motion analysis. Using Tracker, I marked the object's position at each time increment to generate position versus time data. For the computational portion, I created a model in GlowScript to represent an object moving with constant velocity. In the model, I set the net force equal to zero, which means acceleration was also zero. Since acceleration was zero, velocity remained constant. I updated the position using the equation final position equals initial position plus velocity times delta t. This allowed for the program to generate position versus time data for comparison with the experimental results. I used a video of a marker rolling across the table. In lines 26 through 42 of my GlowScript code, I define the physical properties of the system. Here, I assign values to variables such as the object's mass, initial position, and initial velocity. I also defined the net force acting on the object. Since this lab focuses on a constant velocity motion, I set the net force equal to zero. Because F net equals m times a, if the net force is zero, then the acceleration must also be zero. This establishes the physical condition required for constant velocity motion. So this first section essentially defines the physics of the problem. Here, the code simulates the motion over time. The section runs inside a loop that advances the system in small steps. During each time step, the program updates the position using the equation x equals x plus v times delta t. Since acceleration is zero, velocity does not change. Therefore, the object continues moving at a constant velocity throughout the simulation. As the loop runs, the program continuously calculates and stores position versus time data, which is then used to generate a graph. This section represents the computational model predicting the motion. Here, I plotted the time and position data from both methods. For example, at time 0.1 seconds, the experimental position was approximately 0.03 meters, while the computational model predicted about 0.04 meters at a nearby time value. As time increased, both sets of position data increased steadily and linearly. Although the exact numerical values are not identical, both datasets show a clear linear trend which indicates constant velocity motion. However, the overall agreement between experiment and model supports the conclusion that the object moved with constant velocity and that the computational model accurately represents the motion. If I flipped the axes so that positive x became negative x, the numerical signs of the position and velocity values would change. However, the position time graph would still be linear, but the slope would now be negative instead of positive. This means the object would appear to be moving in the negative direction instead of the positive direction. The magnitude of the velocity would remain the same, only the sign would change. What does zero net force mean? In my computational model, I set the net force equal to zero to produce a constant velocity motion. Because of Newton's second law, if the net force is zero, then the acceleration must also be zero. That explains why the velocity remains constant. But setting the net force equal to zero does not tell us how many individual forces are acting on the object. All we can conclude from the motion is that the total of all the forces acting on the object adds up to zero. Overall, the experimental and computational data proved to be very similar. The small differences between the two datasets are likely due to human error during video tracking, slight timing differences, or calibration uncertainty in Tracker. This concludes my Physics 2211 Lab 1 Thank you, and I hope you enjoyed.